Hi everybody. This is the second review for the quiz on Unit 4. And this review matches the test pretty closely in terms of the number of questions and the style of questions. So the very first problem on the test is like this one. So there's one like this. There we go. You will have to draw the triangles and you'll have to use the formula. Remember, you'll be given the identities. Whoa, that's wiggly, sorry. So we've got two triangles, one in quadrant 1 and one in quadrant 2. Quadrant 2 is alpha and quadrant 1 is beta. And so this one would be sine. And in quadrant 2 we have cosine. So this is 5, 13. This is a 5, 12, 13, right, triangle. If you don't know that, no big deal. Use Pythagorean theorem. This one, of course, not a Pythagorean identity. So let's try Pythagorean theorem. So, oh my goodness, 9, that's 3 squared plus x squared is equal to 100. So then we get x squared is equal to 91. And this is kind of what you can expect on the test as well. Some larger numbers underneath the radical. And so don't freak out when that happens. That's going to happen. So let's set this up. I'm going to write out the formula. Sine of alpha minus beta goes sine, cosine, cosine, sine. For me, I need to see where each thing goes. If you want to skip this part, you can, but you cannot skip the next part. So you do need to have all of your parts written out so that we can see that you know the parts, the sine and the cosine and so on. So I'm going to actually put this negative 91 on there, radical 91, just because I know that's going to help me when I go to write down these fractions. Cosine of b, now they told us both of these, so that's kind of easy. The cosine of alpha, this is negative radical 91 over 10. And then the sine of beta is 12/13. And you can see my denominators are automatically a common denominator. This should happen to you as well. If it doesn't, then you kind of already know that maybe you made a mistake somewhere, maybe your triangles aren't correct. So that's kind of a good little midway check. These should not be difficult to combine. They just might be really big numbers. Oops, that's 130. So we have 15 plus 12 radical 91 over 130. And those don't reduce because like 5 doesn't go into 12 and 3 doesn't go into 130 and 4 doesn't. So it's actually the answer. It's just kind of ugly, but it was pretty easy to get to. Then the next two problems on the test are two identities. Now remember, the identities are all problems that you've already done, assuming you've done them all, which I know is a big assume, but if you haven't done them all, I can't really help you, I guess, with that. So these should be something that you recognize. Actually, you should recognize number 3 because we've already done number 3. But so I think we've already done problem like number 2 as well, but I don't know that it was exactly sine and cosecant. But these are all eligible test questions is my point. So for number 2, I'm going to start on the left side, and I'm going to switch everything to sine and cosine. I just feel like I'm going to run out of space, so I'm trying to make more space. So this is going to be, I'm going to put this over 1 just because, I like to do that. And then cosecant is 1 over sine. And then I'm going to do this all at the same time. Cotangent is cosine over sine. And that's kind of this is not a bad problem. If you look, we can make every fraction have a denominator of sine. So this fraction needs to be multiplied by sine over sine. And so now let's fix this. You can see the numerators, if we put all this together, this is your numerator. So this is going to be sine squared x minus 1, that's over sine. And the denominator is cosine over sine. Now, if you're good at your complex fractions, leave it like this. If you're not good at your complex fractions, change it to division. If you're super good at the complex fractions, then you'll know right away that these cancel. Up to you how many steps it takes you from here on out, but you can always switch this to division. now I know that that's cancel, but I'll still write this out. So now we have sine squared x minus 1 times the sine. When you multiply, try to resist actually multiplying. Just write this stuff down, because a lot of times stuff cancels. So you want to be able to see that. Now take a look at your answer. We only want to end up with a cosine. All right, we're trying not to have all this sine stuff in here. So I'm going to switch that. We know that sine squared x minus 1 is negative cosine squared. Sine squared plus cosine squared equals 1. I'm just trying not to write it all out. So we know that cosine squared is 1 minus sine squared. This is in the backwards order from this, so the penalty is a negative sign. And now you can see we get a negative cosine x. If you're not using the trig identities, you're doing something wrong. And this one looks like a monster. It's just full of trig identities. Sine squared plus cosine squared, that's a 1. 1 plus tangent squared, look at the paper. That's secant squared. 1 plus cotangent squared is cosecant squared. So far, all I've done is trig identities. And now I have this down to just words that I know. And so now I'm going to use the reciprocal identities. So cosecant squared is 1 over sine squared. And secant squared is 1 over cosine squared. And of course, this will put our cosine squared on top of the sine squared. And then that, of course, means that this is cotangent squared. I know I stopped working down. I just was going to run out of space. When you use the trig identities, problems like this are very simple. That's the whole point. Now, on the test, there's only one of these, but it's kind of a combination. The problem is more like number 5, but it's not in radians. It's in degrees. So if you kind of put them together, that's really what the problem feels like. Hopefully you're catching what I'm saying. So 75, first thing we have to do is come up with some numbers that equal 75. You know I'm going to use 45. I like that when it ends in a 5. So we know that the cosine is going to be, let's see, 45, and that would be plus 30. And now we use the cosine formula, which goes cosine, cosine, sine, sine. Now in the cosine formula, we use the opposite sign. So 45, 30, 45, 30. So the signs are opposite. By that I mean the plus or minus signs, not S-I-N-E sign. Now we write in what we know. Cosine of 45. Cosine of 30 is radical 3 over 2. Sine of 45. And the sine of 30, of course, is 1/2. And again, you can see, even in a problem like this, we end up with a common denominator. And there we have we know those are the parts. Those are always the parts. We just don't know what the plus or minus signs will be. And so please write that as a single fraction. Now, tangent, of course, has a different pattern of answers. If you don't like the radians, don't do it in radians. Switch it to degrees, which I'll switch to degrees. This is actually 255 degrees. And you know it ends in a 5, so I'm going to use the 45 because I like the tangent of 45. I feel like that's nice and easy to use. So I'm going to need to have the other one be 210, which that's nice. It's on the unit circle, so it works out. So your tangent sum and difference identity, I'm going to write this out. I know you're not shocked by that. Tangent of 45, and this is a minus on the top because we're adding. And then on the bottom, we're adding. And we're going to multiply these together. Somehow I feel like that formula might not be right. So the tangent of 45 is 1. Tangent of 210 over here, positive. 210 is actually a pi over 6 number because it's a multiple of 30. And what is that going to be? 6 pi over? No. 7 pi over 6. So I know that it's radical 3 over 3 is my point because it's got a 6 on the bottom. And then the denominator, of course, is 1 plus this 1 times that same answer. So I'm going to make this a common denominator. 3 over 3 minus radical 3 over 3. And then down here, I don't care about this 1. This is 3 over 3 plus radical 3 over 3. I'm going to write this as a single fraction on the top and a single fraction on the bottom. And as you know, these denominators are going to cancel, or flip, invert, and multiply, or do the complex fraction thing. Lots of ways to get through this. These are gone. Now we have to multiply by the conjugate, which is 3 minus radical 3. The denominator is the boss, and so it is in charge of the problem. The denominator is the difference of two squares. That's the whole point. That's why we have the conjugate. It wasn't an accident, right? That was deliberate. So this is 9 minus 3. The top is a binomial squared. So the pattern is first one squared, then we're going to have 2 of these. We have 2 of these negative 3 radical 3's, so that makes this negative 6 radical 3. And then we have radical 3 times radical 3. And that's a plus. So now we have 12 minus 6 radical 3 over 6. And these can all be reduced. So the answer is 2 minus radical 3. Of course, you can check it, right? Put in this number and see what it is, and then put in the tangent of 255. Should match. All right, now this is where the test is a tiny bit different. Your double angle formulas, you're going to have to do 2 of them. I know there's only 1 here, but there's actually 2 questions. So imagine that we asked for the cosine and something else. It's not 2 different, it's 1 setup, but 2 questions. Sine of 2 theta is super easy. The cosine of 2 theta, you have lots of options. So this should be a kind of a problem that everyone can get right. That's why we put 2 of them on there. So for this, our triangle is in the 3rd quadrant. And we know that the cotangent is 3 over 2, which means the tangent is 2 over 3. This is opposite and adjacent. I guess you don't have to go through that extent to actually figure that out, but these are both negative. I'm going to label them on my picture so that I don't forget to write them down on my problems here. So I'm going to have 9 plus 4, so 13. So radical 13. Remember, your hypotenuse will never be negative, so you don't have to worry about that. And for the cosine of 2 theta, I like the first one, so I'm going to use the first one. You can use whatever you want. I like the first one because it gets rid of the negatives and the radicals. So we have negative radical 3 over radical 13, sorry, and then this will be minus, and the sign is negative 2 over the square root of 13 squared. So this is 9/13 minus 4/13. 5/13. Usually works out pretty smooth. And then finally, the solving problems, the ones that have been around forever, there are 2 of these. There's actually one that you're going to have to factor and one that you won't have to factor, which is nice. Use those trig identities. Oh my goodness. Please, 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 please. This is weird. They have a cosine in common. I don't really know what to do with that. So I'm going to guess that that's probably not the way to do it. Let's switch everything to sine and cosine. What's going to happen here? Let's try to do a couple things at once. Look, these cosines are going to cancel. So I can rewrite cosine squared as something. I can rewrite it as 1 minus sine squared. I'm just trying to do a bunch of things at once because I know that the cosines are gone, so my problem needs to be written in only one word, which is sine. So I'm going to do all that at the same time. So now we have the sine of x, and I'm going to distribute this, minus 2, right? And then plus 2 sine squared x, and then I'm going to bring this 1 over. So let's combine like terms and rewrite, putting this in the right order. So 2 sine squared x plus the sine of x, and then negative 2 plus 1 is a minus 1. And now we factor. The only way to get 1 is 1 times 1. We've actually factored a problem like this before. The setup was different. The beginning part was different, but this part we've actually done. We did in class the other day. So outside we get a positive. So this is where we want the positive, and then this will be a 2, right? Minus 1. So then we have that the sine of x is equal to 1/2, and the sine of x is equal to negative 1. Now remember, you will have your calculator for the whole test, so you could put this in your calculator. That'll tell you 30 degrees here. But your answer has to be in radians. So we're at 5 pi, or pi over 6 and 5 pi over 6, first and second quadrants. And sine is negative 1, of course, straight down at 3 pi over 2. Number 8, we actually just did this one in class as well, this exact problem. Sine of 2 theta, only one choice. 2 sine theta, cosine theta. This has a greatest common factor, which is what I tried to do here. It just didn't work out so good. That's all right. So take out the sine, and we're left with 2 cosine minus 1. So we get that the sine of theta is equal to 0. 2 cosine theta minus 1 is equal to 0. Add the 1, divide by 2. So sine is 0 at 0 and pi. And cosine is 1/2 at pi over 3. And we want to put it in the fourth quadrant as well. Pi over 3. Ooh, said 6. I know I was going to end up writing it. Pi over 3 and 5 pi over 3. Of course, fourth quadrant. All right, last one. 2 sine squared. I'd rather work with the double angle formula. I know we could change both sides. Try not to change both sides. That's feels like too much work. So I'm going to leave this alone, even though I could change it. It's this cosine of 2 theta that seems a little bit more pressing, a little bit more important to change. And I'm going to use the 1 minus 2 sine squared theta, because that matches my sine squared on the other side. So we're going to add 2 sine squared. All right, they're like terms, so we get 4 sine squared theta equals 1. Divide by 4. So sine squared of theta is equal to 1/4. Now we take the square root. So we get that the sine of theta is positive and negative 1/2. So I told you earlier we have one that's factoring and one that's not factoring. This is an example of one that is not factoring. So we're dealing with all the pi over 6's in every single quadrant. So second quadrant, and then 7 pi over 6 is third quadrant, and 11 pi over 6 is the fourth quadrant.